All right, in this introductory problem that involves using Newton's laws for an object that looks like it's hanging and it is not moving, and I want to find the tension in string 1. So I am going to start by drawing in the tensions, which include the directions that are acting kind of at the knot location in the picture. So I have the two ropes, one attached looks like to a wall and the other a ceiling, and then I have a third rope that is going to have a tension in it due to the mass that is hanging below. And the weight of that mass will be m times g. Now, we don't usually draw our free body diagrams directly on the picture. I just did that in this situation so that you could see where I was getting those vectors and those directions from. We usually draw our free body diagrams just kind of as a standalone figure that is coming from a single point, whatever point we're interested in. I didn't draw it in the figure, but if I place my origin, which is what I'm doing, at the location where the dot is in my figure, I can see that T1 lies directly along the positive x-axis and the weight lies directly along the negative y-axis. So I will need to resolve T2 into the x component and the y component. And I'm going to do that by using those angles that were given to me in the problem. Making a table where you put all of the forces and their x and y components is a really great way to make sure that you don't forget anything that needs to be included in your calculations. All right, so my columns will have the x component and the y component, and my rows will have string 1, string 2, and the weight due to that hanging mass. So the force due to that mass acts straight down, so the x component will be 0, and the y component is going to be negative, because it's down, m times g. T1 lies directly along the x-axis, so its y component will be 0, and its x component is just going to be positive T1. Finally, I'm going to put the x and y components now of T2 into the table. So the x goes in the negative direction, so I need to put a negative sign in there. And the y is in the positive direction, so it'll have a positive sign. The x is negative T2 times sine of 60 because it is opposite that 60-degree angle. And the y component is going to be T2 times cosine of 60 degrees because Ty2 is adjacent to the 60-degree mark, or the 60-degree angle. Okay, now we're going to add up all of the x components to get my resultant in the x direction, and then I'll add up all of my y components to get my resultant in the y direction. And I'm going to be using Newton's second law. So the sum of the forces in the x direction have to equal the mass times the acceleration in the x direction. So there is my sum of the x component forces, and that is going to be equal to 0. Then we'll sum up the forces in the y direction. So the sum of the forces in the y direction has to equal mass times acceleration in the y direction. So Newton's second law just in the y direction instead of the x direction. So there's my sum, and that is going to be equal to 0 because it has no acceleration. That's why both of those equal 0. No acceleration in either the x or the y direction. Now at this point, I have two equations and I have two unknowns. So this is solvable. From here, it's just algebra. I am going to take the y Newton's second law equation and solve it for T2 first. Next, I will grab my x component, Newton's second law equation, and I'm going to solve it for T1 using the value that I just obtained for T2. All right, I put that in my calculator and I get 34 newtons. I'm just going to hop up here and check how many sig figs I had. I only had one sig fig in the angle that I was given. There's no decimal point there. So 30 degrees only has one sig fig. So my final answer to one sig fig is going to be 30 newtons.